Welcome back to the deep dive where we take your sources and really zero in on the essential knowledge you need. Today, we're plunging into a particularly neat corner of data structures. We've got a source here exploring a less intuitive way to represent tree structures.
Yeah, those ones usually built like a family tree, right? Linked nodes, pointers, connecting everything.
Exactly. But instead, we're looking at how you can represent them using something much simpler, basically just an array, a list. So our mission for this deep dive is to crack open exactly how this array representation works, why you'd sometimes choose it, maybe over the standard linked way.
And what the limitations are, too. That's important.
Absolutely. So you walk away with, hopefully, a really solid understanding that actually sticks. Let's get into it.
Okay, so thinking about trees in computer science. Yeah, most people picture those nodes connected directly, one pointing to another, like you said, a web.
Right, like node A has a little signpost saying, my left child is B, my right child is C. Very explicit.
Precisely. Each node holds its data and then references, pointers, to its children, maybe even its parents sometimes.
But the fascinating idea this source digs into is this. Can we just take all the nodes from a tree and just line them up sequentially in an array?
And the key question then becomes, can we still figure out all those parent-child relationships just from where a node sits in that list?
Just from its index.
Exactly. Can the array index itself become the key, the map to navigate the whole structure?
So the index sort of becomes the connection info, replacing the pointer.
That's the fundamental idea. Yeah, it's a clever trick, really.
Okay, so where does the source start showing us how this actually works in practice?
Well, it starts with the simplest case, the ideal scenario, you could say, representing a perfect binary tree.
Yeah.
And the source uses figures 712 to show this. It's a tree where every single level is completely full. All the leaves are at the same depth, like a perfect pyramid shape.
Gotcha. Dense. Symmetrical, no missing pieces anywhere.
Exactly that. And for this specific type of perfect binary tree, you can map the nodes into an array really cleanly using what's called a level order traversal.
Level order, right? That's where you go across each level, root first, then the next level, left to right, then the next.
Exactly. You list the nodes starting from the root, then all nodes on level 1 from left to right, then level 2, and so on.
So the root goes into array index 0. Its kids are at 1 and 2. Their children fill up 3, 4, 5, 6.
Yeah.
Just fill in the array sequentially.
Precisely. And because you have this perfect packing, this level-by-level filling, there's a consistent mathematical relationship, an arithmetic link between a node's index and where its relatives are.
Ah, this must be that mapping formula the source mentions.
It is. It's quite elegant, actually, and really central to understanding this whole technique. If you have a node stored at index in your array, its left child will always be found at index 2i plus 1, and its right child will always be at index 2i plus 2.
Wow, okay. That's incredibly neat. So if I'm at the root, index 0u part, left child is 20 plus 1, which is 1. Right child is 20 plus 2, which is 2. That fits.
Yep.
And if I'm at index 1, its left child is 21 plus 1 plus 3. Right child is 21 plus 2 equals 4. That totally lines up with the level order sequence we just described.
It does, and you can easily go the other way, too. Find the parent.
How?
The parent of a node at index I can be found at index I'm1, 2, using integer division, where you just drop any remainder.
Okay, let's try that.
Yeah.
Node at index 3.
Yes.
This parent is 6, 1, 2, which is 5, 2. Integer division gives 2. Perfect.
See? It works consistently.
That's genuinely clever. These simple formulas, just basic arithmetic, they completely replace the need to store and follow explicit pointers. The position tells you everything you need to navigate the tree.
Exactly. You navigate the structure purely through index calculations within the array itself.
Okay, I get how that works for a perfect full tree. But, like the source points out, perfect binary trees are, well, they're a special case, right?
They really are.
Most real-world binary trees aren't perfect. They have missing nodes, gaps, null spots, whatever you want to call them.
That's right. And this brings us to the crucial challenge. If you only store the nodes that actually exist in the tree, just following that level order sequence, you lose the structural information. The sequence of just the existing node values isn't unique anymore.
What do you mean, not unique?
Well, figure 713 in the source shows this perfectly. You could draw two trees that look quite different structurally, but if you only wrote down the nodes that are present in level order, they'd produce the exact same list of values in the array.
Okay, I see. Because you wouldn't know where the empty spots were supposed to be. Like, was the missing child on the left, or was it the right? Or was a whole subtree missing?
Exactly. You can't reliably reconstruct the original shape just from that sequence of present nodes. The ambiguity kills it.
So how do you fix that? How do you represent any binary tree using an array uniquely?
The solution, as the source details, is you have to explicitly account for those missing positions. You have to include placeholder values in the array.
Placeholders. Like what?
Yeah, for every position where a node would exist in a, let's say, complete binary tree of that same height, but doesn't in your specific tree, you put something there to mark the absence.
What kind of something?
The source shows examples using none, which is common in Python, or null, like in Java or C#. Sometimes you even see a special sentinel value, like int_max in C++ code, just some value that you know means empty spot.
So instead of the array just being, say, A, B, C, D, F, H, it becomes something like A, B, C, D, none F, none H, none. You're literally filling in the blanks in the level order sequence.
That's precisely it. Figure 714 in the source visualizes this really clearly. By inserting these placeholders, these none values, the level order sequence stored in the array becomes a unique signature for that specific tree's structure.
And you still use the same index math, like 2i plus 1 and square top 2.
You still use the same formulas to find potential child locations. But now, when you calculate a child's index, say jj equals 2i plus 1, you also have to check, is array one of those placeholder values?
And if it is a placeholder, you know that child doesn't actually exist. That branch is empty there.
Exactly. The placeholder tells you the connection is missing.
Okay, that makes total sense for preserving the structure.
Yeah.
But, it seems like if you have a tree with lots of missing branches, like a really sparse, spindly tree, that array could get pretty big, right? Filled with mostly knowns.
It absolutely can, and that's a major drawback we'll definitely circle back to as a limitation.
Right.
But the source does highlight an important middle ground, a kind of happy medium tree type that works particularly well with arrays, maybe even better than just any binary tree.
And that is?
The complete binary tree.
Okay, complete binary trees. How do they fit in, and why are they such a good fit for this array thing?
Right, so a complete binary tree. Based on how the source talks about it around figure 715, it's a binary tree where every level is completely filled except possibly the very last level.
Okay.
And critically, on that last level, any nodes it does have are filled in strictly from left to right. There are no gaps until you get to the very end of that level.
So thinking about the level order traversal.
There.
Any missing spots, any knowns, they only appear at the bottom level, and they're all clustered over on the right-hand side.
Precisely. All the actual nodes come first in the level order sequence,
Right.
and then any conceptual knowns are just tacked on at the very, very end.
Ah. And that must be why they're efficient for arrays.
Exactly, because all those placeholders, all the knowns, are guaranteed to be at the end of the level order sequence you'd conceptually build. You often don't even need to store them in the array explicitly. You can just store the array containing only the actual node values.
And you just know implicitly that any index you might calculate that goes beyond the end of your stored array corresponds to one of those missing none nodes.
That's the idea. It's a neat optimization. You save space by not storing all those trailing placeholders.
That makes sense. So this is why things like heaps, which are usually complete binary trees, are so often implemented with arrays.
Exactly. It's super space efficient for that specific, quite common tree structure.
Okay, so the strategy for array representation kind of adapts. Perfect trees are simple. Any tree needs explicit placeholders. But complete trees are this sweet spot where you can sometimes drop the trailing placeholders.
Correct. That's a good summary. And the source then gives us a peek under the hood, how you'd actually use this array representation to do standard tree stuff, tree operations.
Right. How does that work? Like, how do you get a node's value or traverse the tree when it's just numbers in an array?
Well, looking at the code structures they provide in the source, you can see how the logic translates. Getting a node's value, given its index size, is basically just accessing array.
Simple enough.
But crucially, you need a check, often wrapped in a helper method, maybe called val, like in their examples. This check handles cases where I might be out of the array bounds, or where array is one of those placeholder values, like none. You need to handle that gracefully.
Okay, makes sense. And finding children or parents?
Just use the index formulas we already talked about.
Right.
Left I returns 2i plus 1, right parent returns 2i returns. The functions just do the math.
So instead of writing code like current node.leftchild.get value, it becomes more like get value index, left current index, assuming get value index handles the none check.
Exactly that. You abstract away the placeholder check inside helper functions, And traversals work similarly.
How do you do something like a depth-first search on an array? That seems weird.
It feels a bit weird at first, yeah. But you still follow the same logical structure. Like for pre-order, visit the node, then recursively go left, then recursively go right. But the moving part isn't following a pointer. It's calculating the index of the left child using the formula and making a recursive call with that index, then calculating the right child's index and calling recursively on that.
Ah, I see. And you know when to stop or backtrack.
You stop when you calculate an index that's either out of the array bounds or when you check the value at that calculated index and find it's a placeholder, none. That tells you the branch ends there.
Got it. And level order traversal must be super easy.
It's almost trivial. You just iterate through the array from beginning to end, maybe skipping the placeholder values if you only want the actual nodes.
So the core tree algorithm's the logic stays the same. It's just the mechanism for navigating that changes. From pointer following to index arithmetic.
Precisely. It's mapping that abstract tree logic onto a different underlying memory layout, a flat array.
This array approach, it feels quite different, definitely, from the traditional linked list style with nodes and pointers. Given that, why would someone actually choose the array representation? What are the big advantages?
The source outlines several really competitive reasons. A major one is how arrays are stored in memory. They're contiguous. All the data is packed together, one element right after the other.
Okay, why is that good?
It's incredibly important for modern computer performance because it's what we call cache-friendly.
Cache-friendly.
Yeah. When your computer's processor needs to access one element from the array in main memory, it doesn't just grab that one element. It usually pulls in a whole block of nearby memory elements into its super fast cache.
Ah, okay. Like a little temporary storage shelf right next to the worker.
Exactly. So if the next piece of data the processor needs happens to be in that block it already fetched, which is very likely in an array traversal, it can grab it from the super fast cache instead of going all the way back to slower main memory.
Right. So if the data's all lined up together, accessing consecutive elements is much, much faster. Like keeping all your tools for one specific task right on your workbench, not spread across different rooms.
That's a perfect analogy. This spatial locality can make array-based traversals, especially level order, significantly faster because the data is likely already in the cache when the CPU needs it. Fewer trips to slow memory.
Okay. Faster access due to memory layout. That's a big one. What else?
There's also a potential space saving. Think about the linked list nodes. Each node has to store the actual data, plus explicit pointers memory addresses to its children, maybe its parent.
Right. Those pointers take up space themselves.
They do. They add overhead. In the array representation, you don't store explicit pointers at all. The connections are implicit, just derived from the indices using math.
So less overhead per node.
Potentially, yes. This can result in a smaller overall memory footprint, especially if the tree is dense and the data values stored in the nodes are relatively small compared to the size of a memory pointer.
Okay, less overhead. And you mentioned a third one?
Random access. If you know the index I of a node in the array representation, maybe you know you want the fifth node in level order, you can jump directly to its data at array. That's a constant time operation, O1.
Whereas with a linked list, even if you know you want the fifth node conceptually, you usually have to start at the root and follow pointers down to find it, right? Which takes longer proportional to its depth.
Exactly. So if your application frequently needs to access specific nodes directly based on their conceptual level order position, the array is much better for that specific task.
Okay, those are strong points. Cache friendliness, potentially less space overhead, fast random access. Seems good. But there have to be downsides, right? When is the array representation not the way to go?
Well, absolutely. There are significant limitations, and the source details these two. Probably the most prominent one is that contiguous memory requirement we touched on.
Right, needing one big chunk.
You need to find and allocate one single continuous block of memory that's large enough to hold the entire array. And remember, that array has to be big enough for all the nodes and all the placeholders for missing nodes, potentially down to the lowest level.
So for a really, really large or deep tree, finding one giant chunk of free memory might just be impossible, even if you technically have enough total memory scattered around.
Precisely. Memory fragmentation can make large contiguous allocations fail. A linked list, on the other hand, is more flexible. It can allocate its nodes piece by piece wherever there's small bits of free space.
Okay, big contiguous block needed. What's another downside?
Modification operations. Specifically, inserting a node or deleting a node.
Yeah. Arrays aren't great for that usually.
They really aren't here either. If you need to add or remove a node, especially somewhere in the middle of the tree's conceptual level order sequence, which means somewhere in the middle of the array, it usually requires shifting a whole bunch of subsequent elements in the array, either to make room for the new node or to close the gap left by the deleted one.
And shifting elements in an array is slow, right?
It can be very slow, potentially an ON operation, where n is the number of elements you have to move. In contrast, adding or removing a node in a linked list is often much faster, usually O1 time, just updating a few pointers.
Okay, so if your tree is dynamic, changing a lot, nodes coming and going frequently, the array approach could become really inefficient performance-wise.
Generally, yes, it's much better suited for relatively static trees.
Got it. Any other major ones?
Well, there's that space utilization issue we talked about, especially with sparse trees.
Right, the non-placeholders.
If your tree is very sparse, lots of missing nodes, long spindly branches, the array representation needs placeholders for every potential spot up to the depth of the deepest node.
Even if most of those spots are empty.
Exactly. So the array can become very large, but most of it is just filled with these known values that don't represent actual data. It's wasted space.
So compared to a linked list, which only allocates memory for the nodes that actually exist, the array could be much less space efficient for sparse trees.
It certainly can be. It's that double-edged sword on space. You save memory by not having pointers, but you might waste a lot more memory on placeholders if the tree isn't dense like a complete or perfect tree.
Okay, that's a really key trade-off to understand.
Definitely.
So let's step back and kind of bring this all back to you, the listener. Why does understanding these different ways to represent a tree array versus linked list, these trade-offs, why does this actually matter?
Well, because choosing the right data structure and the right representation of that structure is absolutely fundamental to building efficient software. It's not just an academic exercise. The way you decide to store your tree data, whether it's pointer-based nodes scattered in memory or a contiguous array using index math, it has a really profound impact on how fast your programs run and how much memory they end up consuming.
It sounds like it's about knowing which tool in your data structure toolbox is the best fit for the specific job you have. You need to consider the nature of the tree itself.
How dense is it? How big will it get?
And also what operations you'll be performing most often. Are you mostly just reading from it? Or are you constantly adding and deleting things?
Exactly. If you're working with a tree that's relatively static, doesn't change much, and it's pretty dense, maybe like a heap or some perfectly balanced structure, and you need really fast lookups or traversals,
then the array might be great.
Then that cache-friendly, pointer-free array approach could be ideal. Its advantages really shine there.
If you have a tree that's constantly being modified, nodes added and removed all the time, or if it's naturally very sparse with lots of empty branches,
then the flexibility of the linked representation, where insertions, deletions are cheap, and you only pay memory costs for actual nodes, no placeholders. That often makes it the superior choice, despite the pointer overhead and potential cache misses.
So understanding these nuances lets you make informed design decisions. Decisions that can significantly affect the real-world performance and scalability of your code.
Absolutely. It's that piece of knowledge that helps you look at a problem and think, okay, given the specific situation, what's the smartest, most efficient way to actually structure my data in memory?
That was a fantastic deep dive, really unpacking how a simple array can mimic a complex tree structure using just basically arithmetic.
Yeah, the index math is the key.
We've uncovered that core trick, seen how it adapts to handle different tree types, from a perfect ideal to handling any tree with placeholders, and that complete tree sweet spot.
Yeah. And looked at how the operations translate.
Right. And importantly, weighed those crucial performance and space trade-offs against the standard linked approach.
It really does show the power and the limitations of mapping these abstract logical structures onto different concrete memory layouts. Each layout has its own strengths and weaknesses.
Definitely. And, here's a thought to leave you with, something to maybe ponder beyond what we covered directly from the source.
Okay.
Even knowing that space inefficiency problem for very sparse trees when using an array, are there perhaps some niche situations where you might still choose it over a linked list?
Interesting question.
Could specific factors, maybe things like the underlying hardware architecture or really predictable memory access patterns, or even just the sheer simplicity of implementing the array version in a particular environment, Could those sometimes outweigh the pure space concerns caused by storing all those placeholders? What else might tip the balance in an unexpected way?
That's a really insightful question to chew on. When might the rules have exceptions?
Exactly. Well, that's it for this deep dive. We really hope you walk away with a clearer, more solid picture of this intriguing data structure technique.